Welcome to Beyond the Qubit. Today I have a special guest, Alexander. And Alexander is very close to the superconducting companies. Alexander works for kiutra, and kiutra is a cryogenic cooling company. And cryogenic cooling is a very important bottleneck, especially for superconducting, but also for spin qubits. So I'm glad that you are here. Thank you, Alexander, for being here.
Thanks for the invite. Pleasure to be here.
Maybe as a starter, Alexander, could you give a 2-minute pitch why investors should pay attention to kiutra?
Yes, for sure. So perhaps the short answer is because we're building the cooling infrastructure that quantum computing needs to eventually scale. So without reliable, accessible, and also helium-3 cooling, quantum computing roadmaps of all the major players, the IBMs in Europe, the IQM, Google, and dozens of other companies simply cannot be realized. So that's the problem. And we're the only company in the world that is solving this commercially. And to provide a bit more context here. So as you know, if you search quantum computer on Google, so in a Google image search today, what you will get is almost exclusively these nice, shiny, hanging chandeliers, gold-plated refrigerators. That is the dilution refrigerator. So not a quantum computer, but actually the cryostat, the cooling machine. And it is so important for this technology that it has become the visual symbol of quantum computing nowadays. But what is less visible is that these systems rely on a very scarce substance, and that is called helium-3, which is produced almost entirely as a product of tritium decay in nuclear weapon programs. And the global supply is predominantly from US military stockpiles. Now, and even if you put this helium-3 question aside, the dilution refrigerators that are used today are very complex machines. They are slow. They demand special expertise that is becoming increasingly rare as the whole quantum community is growing. And a cooldown takes a day or more. These systems are monolithic, so making the scale out architecturally quite difficult based on this cooling technology. And they cannot be easily configured for the range of temperatures that real-world quantum programs actually need. So the cooling technology for quantum, in my opinion, and that's what we're doing at kiutra, needs to change regardless of the supply chain question. And our answer to this is the magnetocaloric effect. So we're using solid, commonly available and non-hazardous materials and no helium-3 at all to provide the very low cryogenic temperatures needed by the quantum industry. Our technology is called CADR, so continuous adiabatic demagnetization refrigeration, and we're the first and only company in the world offering this commercially. So that's kiutra in a nutshell, so to speak, and I guess we're going into the details throughout the rest of our interview.
Thank you for the 2-minute pitch. Can you introduce yourself?
Sure.
How did you become the CEO of kiutra? And what is your background, Alexander?
My background is in experimental low temperature physics. So I did my PhD, my doctoral work at the Technical University of Munich, TUM, where I've been working on magnetic cooling systems since my time there. That's, by the way, also where I met my fellow founders, Jan Spalek and also Tomek Schulz. Jan then continued on the hardware side, so he today serves as our CTO. And Tomek, who also worked in the same group back at that time, is now our COO. So we all met in Christian Pfleiderer's research group at TUM, who also introduced us to magnetic cooling. So I had never honestly considered founding a company at all or becoming a CEO of a company. And for kiutra, the question who of the three of us should eventually serve as a CEO came down to a few just practical realities. So I had been the longest in the scientific system, so by age and tenure, so to speak. And I had accumulated, therefore, more experience in raising grants, communicating our back then scientific ideas and then turning into business ideas, and also building the relevant external relationships with funders and potential customers. And honestly, I also very much value, precision and detail, which means that I don't shy away from working with contracts, bureaucracy, legal matter. And there's a great deal of that if you're running a company. So while Tomek had been deeply involved in the business planning And Jan made clear that he wanted to stay in the tech development, serving as a CTO. Probably this combination I had, tech background, fundraising experience, and communication skills, with the openness with respect to bureaucratic diligence and legal topics, made it a natural fit for me to become CEO.
Okay, and you started already, if I'm correct, 2016 or 2018?
Yes, we started the company back in 2018 when we spun out from TUM, as we could win a first customer. And then in 2019, we deployed our first commercial product. But of course, we had been working on the technology many years before we spun out.
Mm-hmm. Okay. And how was that in the early days? Because that's the hardest part to start up. Or was that not the case? How did you...
I mean, it was, of course, exciting times. At the very beginning, it was only the three of us. We built our first product that we delivered then to our very first customer, even at the university. So we borrowed an old office from my professor that just moved into TUM and wouldn't use all the offices that he got immediately. So we got like a corner office where we assembled the first machine and built it, just the three of us. And then we quite early realized that to get to the speed and also the independence that we wanted to get in building the company, we had to leave the university. So very early on, we decided that we wanted to spin out, but also move out from the university to focus exclusively on building the company and being faster than it would have been possible when we stayed at the university. And that's also why we decided in 2019 to raise the first VC round, almost so very traditional, I would say, in Germany, by the High-Tech Gründer Fund, the dominant seed stage deep tech investor in Germany. And that allowed us then to move to downtown Munich, and start working in our own office and hire the first people that supported us along this mission.
Why did you decide to start kiutra? What problems did you see that you want to solve for?
So we saw essentially two problems, and they're connected. One is really operational, and the other one is more structural. The operational one is that we have been experiencing ourselves for many years. So if you're running low temperature equipment, cryostats, notably dilution refrigerators in a research environment in your daily work, then you will quickly notice how much time you have to spend to prepare, to cool down your experiments to make them work. And you spend a lot of time on something that actually is not even connected to your real academic work. And if something breaks mid-experiments, you're essentially losing the full cycle. So the method requires a lot of, expert knowledge, I would say, also resilience and trial and error. And we noticed as quantum was emerging as a market that there would be far more people relying on cryogenic infrastructure, cryogenic equipment, that not even have a deep physics or low temperature physics background, but that would have rather a fabrication, an engineering, an electrical engineering or semicon background. And so this level of, let's call it, operational effort and complexity would become a serious drag for the whole community as quantum was growing into an industry from an academic field. And then there's this more structural layer, and that is about the helium-3 dependency of dilution refrigerators. So helium-3 is by far not a normal commodity. As I mentioned in the beginning, it is produced from tritium decay. It's a byproduct of nuclear weapon programs to the greatest extent. And there's no meaningful market mechanisms that would allow to expand the production in response of a growing demand by the quantum industry. And it's actually not what we at kiutra say, but that has been clearly identified as an issue by independent research and other communities. So the supply for helium-3, I would say, is probably the most geopolitically concentrated one of any materials in the quantum stack. And of course, there's a growing demand, and it's growing much faster than any realistic production expansion could keep pace with. And now what we're doing, magnetic refrigeration, is solving those issues simultaneously. So the materials that we're using, these solids, instead of rare gases, do not suffer from any geopolitical dependencies or geographic concentration. And because we're replacing the complex gas handling, so circulation of liquefied cold gases, with a solid state cooling process, automation becomes much easier, much more powerful. So the challenge was not so much the underlying physics, but making this magnetic cooling first continuous and then also commercially really viable and reliable. And that is what took us in the beginning many years. And we started developing this years before we spun out in 2018. The other great advantage that we see and already saw at that time is independent of the helium-3 choke point, the technology allows to provide and engineer the base temperatures and the cooling power exactly where it is needed. And this cannot easily be achieved by dilution refrigerators. So this is another great advantage, and we see that becoming more and more important for larger scale commercial quantum computing systems.
Okay, that's quite a lot. So you mentioned a few things: helium-3 dependency, the problem that you want to solve, and the other one is that you say you can do it locally, you can cool things down. Is that fair? Did I understand that correctly?
I think first it's the ease of use. So using a solid state-based cooling system is so much faster and easier. And you can see this directly in our today's customer base. The systems that we're shipping today are also used, for instance, by even for education training of students that don't have a deep background in low temperature equipment. And that is, of course, possible thanks to a great degree of automation, which again relies on the less complex solid state-based cooling technology. So ease of use, independence of helium-3, and then I think the technical advantage of being able to engineer the base temperature and cooling power specifically to the temperature ranges that are needed by the end user application.
Okay, thank you. That's very helpful. What are the key lessons from your career and from your job?
So,
do you maybe have three bottom-up examples that shaped you as a character and personality?
So I think one is, I believe, a very important one. It's probably a lesson that shaped me a lot, but also many of my colleagues and the fellow founders. And as he's running through everything that we're doing at kiutra, it's about endurance and also resilience, because I really think that's an essential ingredient in building something that is deep tech hardware and that lasts. And I can trace this back further than probably my PhD work or academic career. So it's more like an anecdote. But even when I went to school, a friend of mine, we built what nowadays I would generously call perhaps my first startup. That was like a bakery delivery service for our neighborhood. So I lived in a smaller village and the concept was very simple. So every Friday we go door to door and collect orders and money from our customers, and then every Saturday we got up at 5 in the morning and cycled to the bakery, loaded everything into a trolley and delivered fresh bread rolls right to the people's doorstep. And that was, of course, a lovely idea, but it meant in practice that you had to get up very early at increasingly, unnatural or unreasonable time, particularly as we got older and we were going out Friday nights. So I remember that sometimes we went from parties right into work Saturday morning, but it worked specifically because we were very persistent and we delivered the service right when it was least comfortable. So in the winter and fall month, when it was rainy, when it was snowing, when it was dark, and I learned a lot during that time. So I think a lot about customer-centric thinking, diplomatic communication. For instance, if some of the parcels got really wet during rain in the morning, so you had to escalate and be very diplomatic under pressure if you have to explain that to your neighbors. And I think that later was also confirmed in my academic career. So, and I think that is an idea that is shared by many of my fellow experimental physicists. You have to be, in this discipline, you have to be very humble and you have to repeat essentially what everything that you're trying to build, because if you're building something that is very complex, it almost always fails in the first attempt. So you know that already when you start. And it's not about the failure, but I think it's about learning from that failure and then so systematically improving and then doing it again, doing it in a better way. At kiutra, I would say I'm by far not the only person who went through that school. And I think it is one of the real foundations that's on what we have built. So we have a very strong team that is willing to commit fully and retry all the time without a strong ego and improve based on the learnings and the facts that we get from our failures, so to speak. So I think that is really one of the key lessons. And I think it's perhaps like a superpower of physicists, this very strong resilience that you develop during the academic career.
Okay, thank you. I think it's really interesting. Also, some researchers are really good in doing research, but entrepreneurship, that's a different skill set. And I think did this also create a habit for you to getting up very early, or nowadays you get up later? Are you still getting up every time 5 o'clock in the morning?
Not 5 o'clock in the morning. I get up early, but nowadays I do to prepare the lunch boxes for the kids before I then go to work. So it's a different motivation, but I'm still the first person to get up in the morning in my family.
Me too. Okay. What are your key beliefs, Alexander?
So honestly, that may sound a bit romantic, but I'm still a strong believer in science and tech. So this idea about building tech for good, I really believe that technology and science are the most powerful tools, forces that we have at hand to solve problems, fundamental problems of our societies.
What are the benefits of cryogenic cooling? Is it only for quantum computing, or are there also other end markets?
Of course, it's very important for quantum technologies, notably quantum computers, but it's also relevant beyond that area of application. So cryogenic cooling is an enabling technology, a key requirement for other applications. Think of new space, where you need cryogenic cooling, for instance, to operate sensors and detectors during space missions, for light detectors, for instance, that run at millikelvin temperature. And then, of course, there is this whole large area of industrial gas liquefaction that works at cryogenic temperature. So the gases that are liquefied are, of course, the media that are then later used in many applications to provide the cooling for other purposes. But in order to generate them, you also need cryogenic cooling. And one of the most important areas now and in the future may actually be hydrogen liquefaction, where you need to cool to about 20 Kelvin to make that work. And that is very energy intense.
Okay. Thank you, that's clear. And one of the things what I try to understand, for which specific quantum technologies does cryogenic cooling work? And for which is there less use of cryogenic cooling?
I think it's really essential, crucial for the circuit-based quantum technologies, so superconducting qubits and spin qubits. You need to cool those modalities down to very low millikelvin temperatures to make them work at all. Otherwise, the quantum mechanical effects on which those modalities rely can actually not be used. But it's also relevant for other quantum technologies as they are scaled up. So think of trapped ion chips. They may not be operated at millikelvin temperature, but in order to scale them to useful numbers, to build practical quantum computers with that, you still require Kelvin temperatures at least. And we do have customers for whom we are building cryostats to operate trapped ion chips at those temperatures too. And I think the same will hold also for neutral atoms. So right now, this is still a less mature technology, and people try to build larger scale systems that operate at elevated temperature. But I'm anticipating that, like in trapped ion quantum computing, also the neutral atoms at some point will start running on a cold recipient. So of course they already use laser cooling to cool down their qubits, their neutral atoms, such in a similar manner that the trapped ion community is using laser cooling for their trapped ions. But in addition to that, they will also rely on bulk cooling to reduce the black body background radiation, and like in trapped ion computing, improve the vacuum, which is of course, a fundamental requirement, vacuum quality for these modalities.
And why is that? So why, if ion trapped and if neutral atom, if they want to scale up, why is it then that the cryogenic cooling requirements increase?
Yeah. So
what I like best is enablers that win with multiple technologies. So
yes.
if it's so you have exposure to superconducting and spin qubit, so that's great.
Yeah,
but then,
of course, the same cooling technologies are also used, for instance, for NV centers in artificial diamond. They also need to operate at low temperature, and they also require typically magnetic fields which again then demand cryogenic temperatures to operate, for instance, superconducting magnets. But to answer your question about the atomic qubits, I think it's quite obvious for the vacuum requirements. So good vacuum.
And why is that? Can you explain it?
Yeah, so if you trap an ion or a neutral atom and you want to run calculations with them, you really need to protect them from other objects like residual gas atoms in your recipient, in your quantum computer vessel, so to speak. And the cooling the recipient to cryogenic temperature improves the vacuum conditions dramatically. And the reason for that is that then the surface of the recipients become cold and any residual gas freezes out on those large surface areas. And just the probability, so the likelihood of a residual gas molecule hitting your trapped ion or your neutral atom out of its grid is dramatically reduced. And of course, this is not a big issue if you have 5 or 10 or perhaps even 100 trapped atoms or ions. But if you want to go to thousands and 10,000s of them, then probability hits you hard. So you need to ensure very good vacuum conditions. And cryogenic cooling is one of the methods to do that. For neutral atoms, it's also about the background radiation, black body background radiation that goes with the power T to the 4. So the lower your recipient, the better your background radiation and the better the performance of your quantum setup will be. And that is why many companies working in this area already explore cold setups, even for those modalities. Yeah. So of course they're not operated at millikelvin. So the cooling effort, the complexity is much lower compared to, say, the spin qubits or the superconducting qubits. But you also must not forget that those atomic modalities, they add additional complexity. Think of the vibration requirements that are very tough. The ability to combine cooling with optical access, which typically is mutually exclusive. So if you want to keep something cool, you don't want to drill a hole in your cryostat, but you need to do that to run cryogenic neutral atom or trapped ion setups. And then, of course, and that is probably the toughest one, think of the lasers that are needed to build and scale those setups. I think they are much harder to procure nowadays than any cryostat you would actually need. I question a bit that the operational effort for those atomic modalities can be substantially lower compared to the cryogenic circuits made from superconducting or spin qubit systems. And of course, for those, the largest infrastructure complexity originates from the cooling, and this is essentially what we're solving. So that's why I don't see down the line a major issue in this one.
Okay. And the selling price of a cryogenic cooling refrigerator, how does it differ if you have to cool down for longer term for spin qubits and superconducting versus a neutral atom or ion trapped?
Yeah, of course.
Is there a massive difference?
There is a difference for sure, because the less complex Kelvin setups, they are not demanding either dilution cooling using helium-3 nor magnetic refrigeration, but you can actually achieve that with off-the-shelf commercial cryocoolers. But you have to combine that with not so much off-the-shelf vacuum technology, optical access, vibration isolation. That is also one reason why we are building such setups, because you cannot easily get them. It's not yet a standard environment you could get off-the-shelf easily. So overall, those are the price tag will be smaller for such setups. but it's still substantial, while the price tag of a millikelvin system, depending of course on the size and cooling power and of course the actual use case, whether it's in characterization, testing, qualification, or long-term operation, will be larger. So here we're talking about $500,000 to several million euro per installation per deployed system, while the atomic setups are much cheaper. But you have to add additional costs for the rest of the setup, notably the laser setup.
Alexander, I'm not sure if you're comfortable answering, but how do you see the probability of spin qubits and superconducting qubits winning versus neutral atom or ion trapped and photonics quantum computing?
I mean, of course, I have an interest in this answer or in this question because we're a cryogenics company. So to some extent, our largest competitive mode, I would say, lies in the millikelvin cooling. But as I mentioned earlier, we're also building cryogenic setups for the atomic modalities. So we're really not so much depending on who eventually would win the race. And I'm not so sure that, at least in the near term, I don't believe that there will be a clear winner. So I think you really cannot tell right now which modality would eventually be the predominant one. I think in the near term, you just cannot say. The atomic ones, from my perspective, are a bit less mature compared to the tailored ones. So the circuit ones that require the very low cryogenic temperatures. My personal, and I stress here, personal opinion is that the cryogenic modalities, the spin qubits and the superconducting qubits, may eventually capture the largest share of the market because they have the great benefit of being tailored quantum objects. And I think that is, of course, now in the scale-up phase, a big challenge because everybody is struggling with scaling their quantum chips to build more higher fidelity and larger quantum processors. But the benefit is once you have that, you can actually tailor your systems. So you can tune fabricability, you can tune how the chips work, interconnectivity, and you can benefit from the established fabrication methodologies from the semicon industry, which I believe will be a requirement for practical fault-tolerant quantum computing at scale. And if I compare that to the atomic modalities, of course, the biggest advantage of them is that they can easily increase their qubit count because the qubits come just naturally. But the problem with that is that, well, the qubits are just as nature makes them. So you cannot adjust them to your specific requirements. And so since they are so robust, made by nature, you also cannot easily manipulate them. And you need to manipulate your qubits if you want to run eventually useful calculations on a QPU with it. Yeah, so that is why I think down the line, not in the near term, but down the line, some years from now, I do see the cryogenic setups have the greater advantage since they can benefit from both the fabrication lines and the ability to tune the qubits.
Okay, that's clear. Thank you. In the show, we also had a guest, the CTO of Emergence Quantum, Thomas Oakley, and he was quite bullish about cryogenic compute. He said before quantum technology will happen, we will first see something in between AI and quantum technology, and he called it cryogenic compute. What do you see on this topic? And his point was that also normal computers will benefit if you cool them down.
Yes,
because then you can. Heat is a massive issue at the moment for AI.
Yes, I think I would agree here because I think that's also one of the great motivations and something that pushes quantum quite a bit. The now very fast development in AI and the infrastructure demand that comes with that. So the excess heat of those data centers that are needed to run AI is of course dramatic. So you need a lot of energy to operate AI chips, and you're generating a lot of heat that you have to take care of. And working with cryogenic setups can address this. First by, of course, quantum computing. That is a fundamentally different compute paradigm, I would say. But even if we stick to the classical computing paradigm, going to cryogenic chips that are not built any longer from semiconductor but from superconducting materials may pave a way to faster and more energy effective calculations. And there are companies that are commercializing this right now, and they do need, just as quantum computing, they need access to cryogenic temperature to first develop and then deploy and operate their chips. So I think also for this purpose, in this greater future of compute space, cryogenic cooling will be essential.
Okay, thank you. That's clear. What is kiutra's mission?
Well, our mission is to remove the barriers in cryogenic cooling. So we want to make low temperatures, cryogenic temperatures accessible for everybody, everywhere. So independent of the individual background and expertise for sure, but also independent of vulnerable or unclear supply chains. And that is what we're working on. And that is why we're leveraging our unique cooling technology, because it is offering exactly these two things: easy access thanks to automation and independence of scarce resources that other technologies rely on.
Can we zoom in a little bit on the automation? And what do you mean with the automation? Is this the startup? Because sometimes it can take some time to start up cryogenic cooling, and then at some point it also shuts down. So what do you mean exactly, Alexander, with automation? What exactly is this?
That really, again, depends a bit on are used for the fast feedback, high throughput characterization, testing, qualification of devices, all sorts of quantum devices. So starting really from very simple thin films to, of course, superconducting qubits, resonators, superconducting Josephson junctions, low temperature superconducting amplifiers, connectors, wiring components, anything that is needed along this very complex and broad quantum compute stack to eventually build a quantum computer needs to be developed, tested, quality controlled. And with the L-type Rapid, that's our flagship product, doing this is very straightforward because it's cooling essentially automatically. So the manual interaction a user must have with the machine is limited to very few minutes. So if you're using a dilution refrigerator, the normal mode of operation is you are running the dilution refrigerator. In order to test something at low temperature, what you need to do is you switch off the dilution refrigerator, then you warm it up, you disassemble it. So you're taking it apart, you're removing the vacuum vessel, you're removing the radiation shields one by one to get access to the inside of the dilution refrigerator, where actually the point of the lowest temperature sits. And then you mount whatever you want to test. So, and then you reassemble the whole system again. So you add the shields again, you add the vacuum vessel, then you pump the system, you evacuate it, and only then you switch it on. So the preparation and the cooling takes typically a day or more, and it requires more than a person to do so. And that is a great part of the job that quantum engineers are doing nowadays in the industry. So they are spending a great part of their time just to prepare and run those measurements at cryogenic temperature. And this can now be compared with a fully automatic workflow that we're implementing thanks to our magnetocaloric cooling with the L-type, where you essentially have on top of the fridge sort of an elevator with a door that you can open and where you can easily click in the device that you want to check at low temperature. And it's all automatically transferred into the fridge within just a few minutes. So, of course, also dilution refrigerators can come with top or bottom loading mechanisms, but they still need many, many hours, typically 8 hours or more, to lower the device down into the cryostat and cool it down there to millikelvin, while thanks to our magnetocaloric refrigeration process, we can do this really within minutes and have the device cool down within a few hours. So typically 3 to 4 hours, depending on the base temperature that you want to get to. And this is done all automatically. So you can, the interaction time is 5 to 10 minutes for the semi-automatic loading, where somebody still needs to feed in the device into the fridge. But then this person can leave and actually do something more useful. For instance, evaluating data of the previous run, and just wait for the system to cool down and run the measurements. And once they're done, you don't have to disassemble anything. You can just, within few minutes, take out a device, and within another few minutes, load the next device or batch of devices for testing. So the throughput is much larger. Also, the feedback time is so much shorter. What happens quite often is that you're losing wire bonds, electrical contacts during the cool down process. And now think what happens, how annoying this is if you learn about it 8 to 12 hours after you loaded a device. So you essentially lost a full day or more, and you have to get back on the next day and start all over again. While with our approach, you learn about that just after 10 minutes. And even if you lost a contact, you just unload the device, you fix it, and you load within a couple of minutes, so you don't lose anything essentially, right? So feedback time is better, throughput is much better, and that boils down to, it translates to substantial cost savings, because you can use a single device to get the same throughput where you would need multiple dilution refrigerators if you use the conventional technology.
Okay, that's clear. Let me check if I fully understand everything. So when you say you're automating things, that you mean you automate you explain that running a quantum computer with cryogenic cooling involves certain steps, of which is first you have something in the refrigerator, and then you cool it down. But if you want to look what's inside there, or you want to use what's inside there, then you need to shut down the cooling. It has to be heated up, and it has to be taken out, and then you cool it again. Is that correct? Yes. And that part you automated?
Yes, I think so. That's the predominant workflow, not for the operation of the quantum computer, but in its R&D and qualification process. And you have to keep in mind that you have to do this essentially for almost every part that you need to build a quantum computer. So not only the quantum chip, the QPU, but many other components. That is also why not only the chip manufacturers rely on cryogenic cooling for testing and quality control, but also everybody else that is working in the supply chain. In the operation of the quantum computer, automation is of course also essential. And I think the key point I want to make here is, since we're no longer circulating cryogenic liquids, the possibility to automate the cooling process is much better. So think of magnetocaloric cooling, magnetic cooling, as an electrification of cooling. So, and you can compare this, perhaps it's a bit, perhaps a simplistic picture, but think of cars, right? Think of traditional cars that use fuel in a combustion engine to run, and what it takes to build and then maintain and drive those vehicles. So you need many more components compared to a modern electrical car, where you can avoid the gear drive, where the motor is much easier to build. So a lot of the technical complexity can be removed by moving away from cold cryogenic gases as the agent that provides the cooling, to electrical cooling through magnetocaloric materials. And that is what we're leveraging in all our devices, not only for the qualification and testing purpose, but also for the operational platforms.
And what does it mean for your competitive advantage? So the shutdown time and the throughput, how does it compare to refrigerators that are based on helium-3?
Yeah, so in the qualification and testing space, the throughput is significantly larger. Of course, it will always depend a bit on the measurement that the end user is eventually doing. But if you think of a very fast check that takes perhaps just 30 minutes or an hour, you can massively increase your throughput by switching to an L-type rapid, so a magnetocaloric refrigerator for that purpose. And I think that is where we're already leading in the field. So I think we have a very clear competitive edge here for this specific application. And that is also why we deliberately chose to commercialize our technology in this specific area, and not start from building very large cryogenic platforms for the operation of full stack quantum computers. First, we have a clear edge here. Second, it is an existing and fast-growing market because it is an application that everybody is pursuing nowadays who is involved in the development of quantum hardware. So while we have still just few, say, commercial deployments of large full-stack quantum computers, there's a large number of characterization systems out there, inline, end of line, in academia, in research and technology organization, startups, corporates, and big tech. They all rely on this capability to quickly and easily cool down to cryogenic temperature to develop and commercialize their quantum hardware.
And Alexander, can you quantify the difference?
So for a very simple comparison,
in numbers?
You can get 3 to 10x easily. As I said, it depends. So in terms of throughput, if you want to, or if somebody in the audience wants to check that out, we have actually put online even a calculator on our website where you can just using sliders tune your set up your measurement virtually, so you can specify how long your measurement, low temperature measurement would take, and you can actually see the cost benefit and time benefit you would get from using our solution compared to a traditional dilution refrigerator. And so generally speaking, and it's quite clear, the shorter the measurement itself, the larger the time and also the cost benefit of our solution. Of course, if you're running a measurement that will last 2 weeks or longer, then the benefit of being able to cool down something quickly within a few minutes to hours is no longer the predominant factor in this equation. But most of the qualification tests are actually taking just a couple of minutes to hours. And then the speed advantage and the connected cost benefit are substantial. And they can easily go into the millions.
Wow. Then one clarification. If you say chip testing, what do you mean with that? So in my head it pumps up, okay, Orange Quantum is doing chip testing. Is that what you also do on chip testing, or what exactly do you mean with quantum chip testing?
Yeah, so I think what Orange does is exactly that, quantum chip testing. So they are looking at the QPUs themselves. So really the quantum chip that is then at the core of the quantum computer. But a part of that, there, as I mentioned, many other components that have to be tested and qualified in order to build a full stack quantum machine, a quantum computer. And we're also focusing on providing the access, the capacity to test those devices. And down the line, we will also be looking into the full chip testing, so really the large QPUs with all the connectivity their testing requires. But this is something we're deliberately not offering today because we started building more compact systems in the beginning. And for the larger QPUs, you actually need many wires to connect them and run the chip. This is something that cannot be done with our compact refrigerators right now, but this is something that will be addressed by our upcoming product line, which is the X-Type. So something that we have announced recently in Denver at the AAPS Global Physics Summit. So the X-Type will be our large-scale magnetocaloric cooling platform. It is a fundamentally different architecture compared to what we've and anybody else has been building in the past. And it is designed from scratch to allow the operation of large full-stack quantum computers. And of course, that can also be the platform for the testing and characterization testing of the full QPU, because it takes more space, more cooling power to provide cooling to the many lines, the interconnects, to then address the chip. And it also needs lower temperature, so 20 millikelvin approximately to do those tests, since you're no longer looking at individual qubits or few qubits, but a larger array of then interconnected and manipulated qubits.
Okay, thank you for explaining that difference. So maybe to recap, longer term, and especially if you're newer model, you might look into and combine the chip testing also for the QPU, and at the moment it's predominantly things outside the QPU, but longer term you see that's an attractive opportunity for you to go ahead to go after.
Absolutely, yes.